supplier 1 and supplier 2, what is the probability that one is faulty and that is supplier 1's? What we have found out is the probability that if there were 20 trials from supplier 1 sample alone, what is the probability of one faulty part coming out?
Yeah. Half the sample size. Just make it 10 instead of 20.
No.
Or do we wait to like do 70% of 20?
Brilliant, we can weigh it out. But for that also, we need to find out what was the probability of supplier 2's probability of supplying a faulty part, right? Because in this 20, there is a contribution of supplier 2 as well. So this fault could have come from supplier 2. So what is his probability of supplying a faulty part, right? Can I rub the top panel of it? So this is for supplier 1, what Laura calls A. For B, probability X happening is 20C1 again. Now what is the probability of his supplying a faulty part? 0.2, right? So it's 0.2 raised to the power 1, 1 minus 0.2 raised to the power 20 minus 1. That is supplier 2's probability of supplying one faulty machine part out of 20 he is supplying. The language of probability can be sometimes like reading ancient Greek, but you have to deal with it. Is there any confusion? This is the probability that supplier 1 is supplying one faulty machine part out of 20 he is supplying. This is the probability supplier 2 is supplying one faulty machine part out of the 20 he is supplying. But we are interested in finding out if there was a combined sample of 20 taken from these two, what is the probability that that comes from supplier 1? And that can be derived by probability of X equal to X given X happens is as rightly suggested by the gentleman, weighing it out by 0.7 because he's supplying 70% of the time. So it is 70% of the time he is supplying divided by the total probability of that fault happening, right? Which is denominator gives you the total probability that one sample out of 20 would be faulty from both supplier 1 and supplier 2. So this part is for supplier 1, which is A. This part is for supplier 2, which is B. And we have weighed it out by the percentage of times they're supplying. So 70% of it comes from supplier 1, 30% of it comes from supplier 2. Similarly, the denominator is supplier 1's contribution alone. So this is the probability that 1 out of 20 sample is faulty from supplier 1, and this is the total probability that 1 out of 20 sample is faulty from both supplier 1 and supplier 2. And the ratio gives you the probability, which if you can reflect back is your base theorem. This statement is nothing but the application of Bayes' theorem. Is there any confusion? Laura, now you see how the tree diagram can be jumbled up in complex letters of probability. Yeah? That was really a very promising start. Thank you. Any confusion? Right? You agree with this? Brilliant. If you have noted it down, tell me, I will drop it out. I'll begin by rubbing off this. Okay, so we have completed random variable, mean variance, binomial, and left with Poisson distribution. Can I rub it out? Okay. Can I ask who is the student rep of this group? You. Can you request Sarah to change the tutorial room? Because it's infinitely impossible to teach next to a noisy construction setting.
Yeah, sure.
Yeah? Thank you. It's very difficult to concentrate when it's going on there.
So what did you do in the bottom bit again?
The bottom is the summation of the probabilities of one fault out of 20 supplied by supplier A and that of supplier B. So it's a summation and that's weighted out.
So it's really just 1 over supplier B.
It's supplier A's over supplier A and supplier B. And that weighed out by percentage of times they supply. So just as you would have done, if there were A outcomes and A plus B events, so it's A over A plus B, but that now is weighed out, right?
Yeah.
Okay, so the binomial theorem, as we have now discussed, is probability of X happening out of n trials. Right? This is the formal statement of the binomial theorem. What has been observed is if n tends to infinity, that if the value of n is much, much higher than what we are now considering as 20, if n was 20,000, and if p tends to 0, that's very, very small, so 1% or 0.1%, in that case, the value of probability given out of a binomial distribution would be something in the range of 10 to the power minus 10, which does not have any physical significance. It's possibly the size of an atom. Okay? Yeah, possibly, I'll show you. So that does not have, if I say your probability of getting a 90 in econ 103 is 10 to the power minus 10, you would be aghast, right? 10 to the power minus 10 doesn't have any physical significance. For that, the French mathematician Poisson developed another distribution, which is nothing but putting this in binomial theorem and deriving what it is. I can do that, but it will take you 20 minutes and you'll never be able to use it. So I'll skip that and give you how it looks like. This is how a Poisson distribution formula looks like. Where E is a natural number and you'll find it on your calculators. Lambda is the mean and standard deviation of a Poisson distribution. Lambda is the Greek L. So this is the mean and standard deviation of a Poisson distribution. So E raised to the power negative lambda, lambda raised to the power x by x factorial will give you the probability of x events happening out of n outcomes. So if you have already noticed, in this we do not have n and we do not have p. They have fallen somewhere out when this has been deduced. So the higher value of n and the lower value of p is not reflected in a Poisson distribution.
Is it not times together?
Sorry?
In binomial, they get it when you times n times p to get the mean and then...
Yeah, for binomial, the mean is n into p.
Yeah.